record. Okay. So I think Emily, I think your mic might still be on. If you don't mind just muting yourself real quick. Thank you. All right, let's start. So we're gonna just do these quick predict the product questions, and then we're gonna move into all the other reactions. So today's gonna be very reaction heavy, but that's good. I like that stuff. I hope you guys like it too. So the first thing that we're gonna do is we have this nucleophilic pi bond. We see we have HCl. I think we're pros at this by now, knowing that we're gonna form a carbocation according to Markovnikov's rule on this secondary position. So that would be something like this. Okay, so secondary position, that's Markovnikov's rule. So this is a very characteristic feature of a ring expansion. So you see a 5, or so it's a 3, 4, or 5-membered ring, and you have that vinyl substituent. You always have to have this pi bond adjacent to that ring. And what's gonna happen is we're gonna be able to open this bond, and we're cutting here, and we're opening that bond and sticking it onto there, okay? So if I wanted to number this to maybe help myself out, 1, 2, 3, 4, 5, 6, 7. Okay, so now we went from the benzene ring on the left to a 5-membered ring on the right to a benzene on the left, because we're not doing anything there, and now a 6-membered ring over here. Okay, so now I'm confused about the numbering. So let me I know 5 and 6 are these. Okay, so this is definitely 7, but 7 is now not to 3, 7 should be to 2. So that should be 7 to 2. 4 is fine to be up there, and 3 is fine to be there. And then notice on 2, there's this methyl group coming off, okay? But remember, I pulled electrons away from 3, so that's where my new carbocation is gonna be, okay? Always assume one rearrangement. Yes, you're right to think that I could do maybe a subsequent hydride shift with the hydrogen on position 2, but we're just assuming one rearrangement for your class. Oops, there's a lot of people in the waiting room. Let's accept everybody. Okay, so we're at this, secondary position. We have this carbocation, and then what we're going to do is we take that chloride anion, and then it's going to attack at that position. So the resulting structure is a benzene ring with a cyclohexane, and we have chlorine. Okay, so now when we're thinking about the major stereoisomers of this reagent, excuse me, of this product, we see that we generated 2 different chiral centers. So we have this chlorine that's chiral, and we have this methyl that's chiral. So in terms of picking from a list of all structures that you would be expected to select from on a test, we would do the wedge, we would do the dash, so plus dash. We would do the wedge dash, and then the dash wedge. I don't get to draw those out, but hopefully you guys understand that. Okay, so 4 major stereoisomers for reaction 1. Okay. For 2, so we have a 6-membered ring, and we have this vinyl substituent, but don't be fooled, it's not a ring expansion. Remember, ring expansions are always, hear me say that on the test too, it's gonna be a 3 or a 4 or a 5-membered ring. So essentially, we also talked about what happens when we mix water and acid, and we have to assume that we're adding these 2 together, and that's gonna really form hydronium. So I'm gonna draw this down here. So essentially, we have hydronium, and I showed that last class. All right, more people in the waiting room. Okay, and that nucleophilic pi bond grabs a proton, and that electron density gets retained by the oxygen. Okay, so then the result is a secondary carbocation, because that's Markovnikov's rule, and we're not doing a ring expansion. We're not going to go from a 6-membered ring to a 7-membered ring, because the 6-membered ring is ideal. So what we could do, though, is we could do one rearrangement with this hydride shift. Okay, we can move the hydride over, and then that effectively pushes the carbocation from the secondary position to the tertiary position. I'm just showing the hydrogen so you guys followed where I moved it. Okay, so based on that, we know that water is going to be the main reagent that comes in, okay, attacks at that carbocation position. We're left with, this ethyl group and this now water group. Okay. We always said that we assume excess reagent, so let me just draw another water molecule floating around. And that's gonna, at any given point, collide with this intermediate and remove that final proton to synthesize a final alcohol. Okay. How many products should I draw for this reaction? Labeled 2. If you guys want to put it in the chat box. How many total products should I show for my answer? Anyone? 2. Okay, so the answer is 1. So again, that's why I keep trying to ask this to you guys, because I want to know how well you guys are doing with the chirality and stereochem stuff. So it's really only one product, and this is the one product because this isn't a chiral center. And it's not chiral because we have the left and the right side are both the same thing. So just that one product would be fine on the test. So remember, stereochem is important. That's why I kept saying like over and over again that you guys have to know that, because it affects every single answer moving forward, to knowing like when to write more than one product. Okay, so here we have the final example with HBr. Okay, and the thing here is that we have 2 secondary positions. So whenever we have this situation, and they're both the same in terms of substitution with respect to that alkene, we're going to get a mixture of products. So you could argue that the carbocation is going to form on this position, this position, and it's also going to form on this position. So we would have these 2 intermediates that actually form in 50-50 mixtures. So we would get a carbocation here, and we would also get a carbocation here. And the reason that is because there's no difference in substitution or stability. So it makes sense that logically you could have 50 and 50 and 50% in solution. So we have those 2 intermediates, and we know bromide is going to attack there, and also any other bromide is going to attack there. So we actually get how many products based on this, if you think about it? How many products do we think? We have 2 intermediates. We have an sp2 center that's going to get attacked. Remember, there's a p orbital that are there. You're going to attack from the front face or the back face at this position. Okay, 4. Yep, that's awesome. 4. Yep, you got it. 4. So this is going to stay the same no matter what, because we're not doing any chemistry here on the methyl. But what's changing is the chemistry at this carbocation. So what we're doing is we can attack from the front face. That gives me wedge, or we could have attacked from the back face, which gives me wedge dash. So essentially, I'm going to draw the products down below. So we would get this one, and we would also get this diastereomer. So these 2 products are formed from this intermediate, okay? And then from this intermediate, we also get 2 more products. I'm gonna draw that down here. So it could have attacked from the front face. You also could have attacked from the back face, okay? So these are not, you can't say racemic, and the reason that is because these are clearly constitutional isomers of, well, this top row is clearly a constitutional isomer of the bottom, and also that these are diastereomers with respect to each other, and these are diastereomers with respect to each other. So you definitely can't say racemic. I think I have some questions going on. Let's see, can both intermediates form and they both make products? Yes, yes, exactly. Thank you, Lilis. That's exactly what I was gonna say. Because there's no difference in substitution, Markovnikov's rule isn't going to really apply here. So we're basically going to put carbocations on both of those positions because they're both equal in terms of stability. Yeah. Caroline, do you still need help with that, or?
With 1.
With number 1?
Yeah, I was gonna ask about number 1. I was confused if you did, or why you put that carbocation on carbon 3 there.
So it's actually, this is carbon 2. I put it on carbon 2. And what happened was what I'm doing is when I cut here, okay, I'm literally removing the electrons from this 7-3 bond. So remember last class, I would show this kind of partial positive on 3 to indicate that we're slowly starting to lose electrons there, but we're putting them onto 2. So we're fixing the thing at 2. That's why the 2 doesn't have anything, but we made an issue at 3 by removing them, okay? Hopefully that makes sense.
Where were the final products for that one? Those 2 on the bottom?
Right here. So I didn't draw all of them out, but you would have 4 products because you would have 2 you have 2 chiral centers. You'd have wedge, dash, dash, wedge, dash, dash, wedge. You know, all the combos. Okay. So that's pretty, yeah, hopefully that made more sense. And let's see, we have another question. I missed it. Can you explain again why ring expansion is only for 3, 4, 5 rings? Yeah, so I'm going to actually, fine, briefly, it has to do with ring strain. I'm going to post my old videos and I go into detail with that from Monday's session. So if you can just watch that video again. But ring expansions happen because the same kind of argument with chair conformers. We want to have 109.5 degree bond angles as predicted by the sp3 geometry. So all of these centers are sp3, as you can see. sp3 tells me I want 109.5. 109.5. Clearly, internal, I have 90-degree angles, and internal here, I have 6-degree angles. So these angles differ significantly from what hybridization theory tells us they should be. So that's why we do these ring expansions, because when I go from maybe this I can't think, propane, and I go to cyclobutane, I went from 60 degrees to 90 degrees. So even though it's not perfect, it's still getting a lot closer to that 109.5. Same thing here. I'm pretty sure a 5-membered ring, I know I drew that bad. I think it's 120-degree interior angles. I don't know. Anybody remember geometry from like 8th grade or something? I don't really know how to do interior angles, but I think this is 120. So the point is that you're getting a lot closer to the ideal bond angle that hybridization theory predicts. Okay. So yeah, good. And I go into a lot more detail on that in my last video. So cool. All right, let's jump in at reaction practice. So this is fun. We're going to go to page, I'm definitely going to do number 10 on page 62, but I think I'm going to do that towards the end when we build everything. So let's just do, we're going to be on page 63 and in the student workbook, and we are going to start with 11F. So if you guys look on the student workbook, we have already covered 11A through E. Those would be all the hydrohalogenation reactions, and they include some sort of carbocation arrangements and ring expansions and things like that in there. So be able to do A through E flawlessly. I think you guys have enough information to do that now. And we're just going to touch a little bit more on F and G. So yeah, so we're going to do these acid catalyzed hydration just in a little bit more detail. So we're on 11F. We have this structure. Okay. And we're subjecting this to the acid catalyzed hydration. So again, where does that term come from? Acid catalyzed hydration. So this is reaction 2, and hydration is coming from that, and acid catalyzed. So acid. Okay. So acid catalyzed and water. And what happens is we know these two react first together to form hydronium. So we really have a hydronium in solution. Okay. Same thing applies. That pi bond is going to grab a proton. We're going to follow Markovnikov's rule to form, you know, this is that a 5-membered ring? Oops, this should be a 5-membered ring. Okay. We're going to form that carbocation intermediate on the tertiary position. And then we're going to have water, you know, form an alcohol at that tertiary position. So I'm skipping all the mechanistic steps because I already showed that in the beginning. But essentially, you should be able to get to these two structures pretty quickly in your head. Does that make sense? So like, yes, the mechanism is helpful. Yes, you'll get it right every time if you go through the mechanism, but you do not have enough time on your test to do mechanisms for probably 20 predict the product questions. You don't. So there has to be some degree of you knowing in your head or visualizing it. Like, oh, that I know, I don't need to draw all these steps. I know that I'm going to form a carbocation, boom, alcohol, because that's what this reaction does. And then that's there. Okay. So will we be tested on the mechanisms? Yes, you will be tested on the mechanisms. So I think in years past, you know, obviously in person, you have to write out full mechanisms and you get graded on every structure, every reagent, every formal charge, things like that. So luckily, you guys won't be graded like that this time, you know, this semester. But what I could see happening is her showing like, you know, A through F options or something like that. And you have to select which one has the right set of mechanistic arrows. Maybe which step, like maybe she'll isolate a specific step and say, what are the mechanistic arrows to go from this intermediate to that? So, you know, there can be many different questions in terms of mechanism that she can definitely ask you. Okay. So that would be 11F. Okay, so 11G. And I hope, does somebody have the key pulled up for this one? If they do, please let me know. Yeah, Mary, can you tell me if she puts the alcohol on the benzylic position or if she leaves it on the tertiary position? Just real quick.
She puts it on the tertiary.
Okay, cool. So again, in years past, like we used to do multiple rearrangements, and this is an example of someone that would do multiple rearrangements. But again, I guess from this semester moving forward, she wants all of you guys to just assume one rearrangement, okay? So if we have the same kind of acid catalyzed hydration conditions, okay, we know we're going to form a carbocation on that secondary position. So everybody should get here pretty quickly, okay? And then we're going to assume one rearrangement. So what happens is I can shift this hydride over, and then we get a tertiary position for that carbocation. Okay, that was our one rearrangement. Our alcohol is going to go onto that substituent. So I'm expecting to get a product that looks like this. Okay, and remember that was a chiral center that I just generated. So I'd be expected to show that mean enantiomer and that mean enantiomer. Okay. So again, like the reason why I said this was, you know, in the past, a multiple rearrangement question, you know, we're at this tertiary position, and in theory, you could, you know, shift one more over to get to that secondary benzylic position, which is more stable. But we're only assuming one rearrangement. Okay. Cool. That's G. Okay, so let's do 11H. Okay, so we are at, oops, it's a 5-membered ring. I always do that. I have it. And we have this isopropyl group on a dash. So remember, anytime that we show stereochemistry away from the pi bond, clearly we're not dealing with this isopropyl group, we're going to have to just kind of assume that this substituent is going to stay the same configuration in the starting material and in the product. So according to Markovnikov's rule, this is going to, what is this? This is water and proton. Okay, so water and then proton catalyst. So that's going to form a carbocation on the tertiary position. That's Markovnikov's rule. Okay, and then water comes in and attacks there. So I'd be expecting something that looks like that. So then, again, not racemic and not 50-50 enantiomers. What we're getting here is 50-50 diastereomers. So yes, this is a chiral center. We're going to leave that isopropyl group the same. So you would get something that looks like this. These two structures. So again, half the battle is like knowing what the reaction does. And then the other battle is going to be knowing, are they enantiomers I'm drawing? Am I drawing diastereomers? How many? You know, that's, I guess, a really big thing there. Let's see, question. So it doesn't matter which strong acid you use, right? It's always going to be, yeah. So it doesn't matter. It does matter. I mean, in terms of your class, just anytime you see an acid, like, no, it's acid catalyzed hydration conditions. In terms of the real world, it does matter because the strength of the acid is going to dictate how much hydronium you yield. And obviously you want to yield maximum hydronium to conduct these reactions. Oops, maximum hydronium to conduct these reactions. So the strength does matter in real world in terms of your class and your test. We're never going to trick you and give you like a weak acid and be like, oh, it doesn't work. Like, we would never do that. Okay. But yeah, some food for thought. All right, 11I. Okay, 11I. So we have this, and we're subjecting that to sulfuric acid and water. So again, we're going to get a secondary carbocation over here. And then I can see I can do one subsequent shift. It's an alkyl shift because we don't have a hydride over there. So that makes a tertiary carbocation. And then I'm expecting an alcohol at that position. How many products should I draw, everybody? 1. I love that. You guys are getting better. 1. Okay, because not chiral and not chiral. Okay, 1 product. Cool. I don't know. What do you guys think? Quick poll in the chat box. Do you guys like this second half of the class better than the first half, or do you like the first half better? Yeah, me too. Undecided. Yeah, this is very like mechanism, and it's okay. Some people are back and forth. It doesn't matter, but I really think this makes a lot more sense than the other stuff. We'll see after the exam. I love that. All right, and I'm gonna leave Jay for you guys to do on your own. Okay. So now we're gonna move on to a different variation of that reaction. All right, here's a question from Priyal. Hold on. If there's a chiral center without OH, do we ignore it? Yeah. So like up here, we had a chiral center. This was isopropyl, and we ignored it in the sense that we didn't change any stereochemistry. Okay, if you're not doing any chemistry in terms of reacting there, leave it the way that it is. Okay. I thought I understood it last chapter, and then I didn't do good on the exam. Yeah. I hope that's not the case again. Yeah. I'm sending you all the positive vibes, all positive vibes. All right, so let's go back. So now we're going to try a different variation of this. So this is really the exact same thing that we've seen. Okay, so this is called, I call it acid catalyzed ether synthesis. I mean, that's how I call it. There might be a whole bunch of different names, but for me, it's called acid catalyzed ether synthesis. So the first reaction we had was hydrohalogenation, which is HBr, HCl, things like that. The next reaction we learned was acid catalyzed hydration, which was H2O and some sort of catalyst to make an alcohol. Okay, so maybe I'll just write like, so you guys know what we're making. So this was a haloalkane that was made from HBr. This is an alcohol made from these two. And then now what we're gonna do is we're gonna substitute this water reagent for some sort of alcohol. So maybe like, I'm just gonna call it ROH, and we're still gonna need a proton present, okay? And I think as you guys can tell by the name, this is gonna be an ether that's forming, an ether. So that's like something like that, ethers, okay? Where they're connected by an oxygen single bond. And anything you recommend for dealing with tricky questions where the answer choices are weird? Like honestly, then I would get answers, but the choices are flipped around and were treated weird. So it's really hard to find answers that makes total sense. So essentially, my biggest hint for you guys is like, if you see a structure that isn't what you drew out on paper, what you really can always go back to is assigning R and S in your in your product, and then like that you drew on your paper, and then you can do R and S on the answer choices that she has there, because that's really the only reason why we're rotating. We're rotating to see if you guys still understand that the chirality or the configuration of those things is still the same. So a cheating way to do that essentially is just to assign R and S to the structure you drew on paper, and then assign R and S to all the structures that you see on the answer choices. And the one that matches the R and S is going to be a way that you can match those answer choices up without rotating your structures and things like that. Does that make more sense? Really, always go back to R and S. I think like people forget about that skill, and I really think it's going to help you. All right, moving on. So acid catalyzed hydration. So let me just do a generic example. So I'm going to take this structure and I'm going to subject it to, let's just say, methanol. So this is methanol, and HCl for catalysts. Oops, catalysis. Okay, so essentially what happens is all we did was, so with water, let's analyze these two reagents. So here we have water, for lack of a better, in terms of depiction. So all we're doing between water and this alcohol version of it is we're literally just substituting this H for an alkyl group, okay? And whereas before you saw the OH attached on, we substituted the H now for this alkyl group. So then instead of it being OH, it's just O and the R group that goes on. Does that kind of make sense? And I'll show that in a mechanism in a second. So again, you have to realize that the two reagents are going to mix together first. So that would be something that looks like this. So this is my methanol example. Here is HCl, and I showed this with hydronium before. And that, lone pair is going to grab a proton. And, it looks like hydronium. It's not hydronium, but it definitely looks like hydronium. And this is my main reagent. So and if you wanted like a name for this, this could just be called the protonated alcohol. Protonated alcohol. So it's the exact same thing that we've seen before with acid catalyzed hydration, where water became protonated like that to form hydronium. And now this alcohol is just going to get protonated to form the protonated alcohol, okay? So now this protonated alcohol, let me just draw this again down here. This nucleophilic pi bond is going to grab that proton. We're going to follow Markovnikov's rule to form that secondary carbocation. And then we're left with just plain methanol. Okay? So now plain methanol can come and just attack. Okay? And then remember, we always assume excess reagent, so you assume there's more methanol hanging out. Okay? And then at any given point, that methanol can come close to that proton, remove that final proton, synthesizing an ether. I'm just going to do it like that. So that's my ether. Okay, so the difference between this one and the reaction we just saw was you would have OH here, but because we changed this, like we literally changed one of those groups to a CH3 group, it's the alkyl group that now gets attached. Okay, does anybody have any questions? I think that's pretty obvious in terms of like it's the exact same reaction we just did, like the exact same one. Just now instead of the H, it's this R group. Any questions so far? Okay, Great. Let's just do some examples of that. So we're looking at 11K. So that would be something that looks like this. And we're subjecting that to CH3OH and acid. Okay, so you know quickly that we're going to form a protonated alcohol. This pi bond is going to grab one of those protons from the protonated alcohol, and we're going to follow Markovnikov's rule to form a secondary, I'm just going to draw it over here, a secondary carbocation. This is a very characteristic thing that you guys should know. A 5-membered ring with an adjacent carbocation is going to be, yeah, H2SO4, I'm just abbreviating it as H+. Like it's the same thing to indicate acid, but sure, same thing. Okay, so what happens here is we're going to have a ring expansion. Okay, so we get something that looks like that. And then our alcohol is just going to attack there. And remember that we're going to remove that final proton. So I'm going to skip a whole bunch of steps, and you should synthesize something that looks like that. Okay, how many products should I draw or select on the test in the chat box? This one. I'm going to keep asking this question every time so that you guys start getting it. How many products? Okay, I see 2, I see 2. So the answer is 4. 4. So this is why we're going to keep doing this. So it's 4. So we generated 2 chiral centers in the process, here and here. So we have 2 to the n, 2 squared, 4 major stereoisomers. So that means you need to draw wedge, wedge. You need to draw, I'm going to do this for you guys so that I think it's more clear. Wedge, dash, dash, wedge, and finally dash, dash. Oh, I think it's that. So those would be all the ones that you would have to select from like a drop-down list on your test. Okay, exactly, Caroline. That's great. And that's why I emphasize, everybody look what Caroline just said. Do we always look to do a ring expansion, any reaction if we have a 3, 4, 5-membered ring and a carbocation? Absolutely, every time. Remember that that carbocation specifically has to be adjacent, so 1 carbon removed from the ring in order for that expansion to happen. But yes, that's very important. All you guys should know that anytime you have a carbocation intermediate, especially with a 3, 4, 5-membered ring, always ask yourself, is there a ring expansion? Great, great question. Okay, I thought you said you ignore the other chiral center. I think I misunderstood it. Okay. So yes, you ignore the original chiral center if we already indicated some chemistry there. But what happened was that in this starting material, it was achiral, and then through the ring expansion, we became chiral. So you see, right now this is achiral. But when I did the ring expansion, now this method became chiral. It's a new sp3 center, and you could argue that it's either to the front or to the back. Okay, so yeah. Okay, well, a lot of questions. Could you go over where you put the carbocation after the ring expansion? Yeah, so again, if this helps you, I would always start, I said this like last time, I would start from the substituent in terms of numbering and go clockwise or counterclockwise, I guess. This is counterclockwise, and go around the ring. So I'm cutting from 3 and 7, and I'm putting those electrons now between 7 and 2. So this should be, okay, so does that numbering make sense now? So if I remove things from 7 and 3, and I'm putting them on 2, that happens there, and then the deficiency was pulling them away from 3. RNS here is not going to help you because there's nothing to really compare. We were talking the RNS thing if it, in regards to like structures, answer choices that are rotated, and how to identify those from the structure you would draw on your paper on the test. Okay, let's keep moving. So we have 11L. Okay, so 11L is going to be something that looks like this. And I think this is the last example I'll do of this, and then you guys can do the rest of them on your own. Okay, so remember this is now, okay, so fun fact, the alcohol you drink is ethanol, so that's this structure. Okay, so any sort of commercially available alcohols are these ethanol structures. And what happens is it gets protonated. You know, we're going to do Markovnikov's rule to form a tertiary carbocation. So I'm at this position, and the alcohol is going to come there. So we're there. How many products should I draw on the test? How many products? One. Yay, we're getting good. 1. So there's an ethyl to the left and ethyl to the right. That immediately is going to tell me achiral. That is not a chiral center. Okay, so one product. I think you guys are getting good at this. So that's it for acid catalyzed ether synthesis. I think you guys can do M, N, and O. N is definitely going to do a ring expansion, so that's a good example of that. And now we're going to move on to the next reaction. So we're on reaction 4 for you guys. And reaction 4 is halogenation. And you might get to, where did you guys get up to today in class, or should be, just so I know? Anybody know what reaction you guys get up to? Oh, cool. Mercury oxidation. Cool. All right, so we're going to definitely do the next 2 reactions for sure today, and we'll see where we get. Okay, so that's the first 3 reactions. No, don't worry about it. Okay, so halogenation. So this is interesting. So this is kind of cool, and I've done this reaction like myself, and it's interesting. It really is. But what happens is we have let me just draw a generic one. So I like to do the same kind of vinyl group, and we're subjecting this to something like we'll call it X2 and some sort of inert solvent. Okay, so X2 just stands for any halogen. So where X could be bromine, chlorine, iodine. Actually, I think iodine might be too heavy, but for I think all intents and purposes, you really only see bromine and chlorine. So we're dealing with now not with HBr or HCl, that's a hydrogen halide. Here we're just dealing with diatomic gas. So we're dealing with Br2 or Cl2. So it's a very different reagent. And specifically, this is the first reaction where we're going to see where we have a solvent kind of written in, where it doesn't do any reaction. I should say it doesn't do any chemistry. So the 2 types of inert solvents you could have is something called dichloromethane. And these are very common. Like when you guys take organic lab, we use these solvents all the time. So that's why, like I said, these names are kind of important. So dichloromethane or chloroform. And yes, if you're like eyes are lighting up, chloroform, like that is the chloroform that like is like abused and used like in not good ways, not legal ways. So chloroform is actually getting the chemical formula CHCl3. Okay, so that's if you guys actually wanted to know what it looked like for fun. Looks like that. That's chloroform, and it's gaseous. Okay, so that's chloroform. So dichloromethane is very similar to chloroform. However, dichloromethane is just 2 chlorines. So chloroform is 3. So dichloromethane would be CH2Cl2. Okay, so just be able to recognize that with these halogenation reactions, we use inert solvents. The reason behind that is what the inert solvent does is it's not going to react with your reagent or your starting material. Instead, what it's going to do is it's going to be like almost a sailboat or like a cargo ship. And you can imagine that these X2 non-polar molecules are going to be pretty well dissolved with these chloroform and dichloromethane inert solvents. So it actually, like, you can think about it as like it drives the X2 passengers towards the alkene. For all intents and purposes, all the solvent does is it brings the reagent close to the alkene. That's all you need to know. Maybe confused on that? Doesn't do any chemistry, except for the fact that it just brings the X2 gas close to that alkene. And there's 2 types. So sometimes you'll see me write DCM. So DCM is dichloromethane, which is that, and this is chloroform. Cool. So something weird happens in terms of the mechanism, and it's the first time we're going to see something called a concerted mechanism. Okay, so concerted. So concerted mechanism. Okay, so before, when we saw all of our mechanistic problems, we were seeing, okay, here's, here is one arrow, here's another arrow. I isolated an intermediate. Then here's another step, and then here's another arrow. So there are multiple steps that are happening, okay? So essentially, this is not a concerted mechanism, okay? So what is a concerted mechanism is when there's more than 2 arrows happening in this, beginning step, okay? So an example of that would be the one we saw above. So I'm going to take this and subject it to Br2, and I'm going to say DCM. Okay, so this is a different reaction we have. And what I want to do is I want to draw Br like this to indicate that it's a diatomic gas. Okay, so in terms of concerted, what that means is that this pi bond, okay, is going to grab this bromine, okay? This, since we exceed the octet now, this bond has to break, okay? But remember that bromine has these lone pairs on them, both of them, okay? So as you do this, okay, everybody, if you're falling asleep, this is the part where you want to pay attention. As you're pulling electrons away from this pi bond, you can see how you get partially positive there, because I'm going to form a carbon-bromine bond here on this secondary position. So I'm forming a carbon-bromine bond at this secondary position with this pi bond. And since I'm taking electrons away from the primary position, it becomes partially negative. Excuse me, partially positive. But what happens, though, in the exact same time is that there's a pair of lone pair electrons from the original bromine that's going to lean over and fix that deficiency. Okay, so this is the concerted mechanism where this pi bond first grabs, this bromine. We exceed the octet of this bromine, so we have to break this bond. And then since this partial positive is developing, any of these lone pairs that were already present on the bromine can also lean in here and stabilize that deficiency. So the intermediate is really something that looks like this. You get, two types of intermediates. And we're going to talk about some stereochemistry stuff in a second. Okay? So these are my two main intermediates. So these intermediates, I think the name is kind of important. These are Helonium bridge intermediates. Okay? These are not carbocations. Okay? So there's a difference here. This is the first reaction with reaction 4, where we do not see any carbocations. We see a Helonium ion, but we don't see a carbon with a positive charge. So for all intents and purposes, all of that discussion about rearrangements and ring extensions does not apply to these types of reactions, okay? So this is the first time we're seeing a different intermediate than the carbocations we've seen before, okay? So remember, this wasn't the only thing that we generated. So we have this intermediate, but we also generated that free bromide, remember? So we have this free bromide hanging out. Okay, so we have that free bromide hanging out. And now that bromide is going to attack, okay? And I'm gonna ask you guys a question in a second. This bromide is going to attack one of these positions. So it's either gonna attack, let's call it position A. We'll call this position B. And what's gonna happen is it's gonna attack in such a way that you're gonna break this bridge and you're gonna get two bromines, one here and one there, and so forth, okay? So in terms of, you guys have the knowledge to answer this question I'm going to ask right now. So when this nucleophile is going to come in, is it going to attack at the A position or the B position? And my hint to you is draw resonance structures, okay? And let me know in the chat box. Okay, I see A, I see B. I'll give you guys a little bit of time. Yeah, okay, so a couple of you guys are responding. Yeah, so the answer is B. So let's explain kind of why that happens. So let's just take one of these intermediates and redraw them below. So I'm here, because I always like proving things to you guys. I don't like when you memorize, so it's important that you guys know this. Because look, you'll be like me, who's like a million years removed from when I first took the class, and you still remember it, okay? So if you understand it, you'll still be able to remember it like years down the line. Maybe that's exaggerating, I don't know. So here we are. So this is the intermediate. I just reproduced it below. So what I want to do is I want to draw a whole bunch of resonance structures, maybe potentially rationalize why I got addition at the B position. So if I were to break this bond, and let's just say I gave the electrons all to the bromine, the resonance structure would be something that looks like, okay? Do you guys all see that? So all that happened was I broke this bond and I gave the electrons to bromine, and then that made it a positive charge there. Okay, so then the other resonance structure I want to draw is, let's just say, I'll draw it in blue, I broke this bond. Okay. So then the structure would be something that looks like this. Okay, so we have three contributing structures to this Helonium bridge. Okay, so these are the resonance structures for this. All right, so now let's go in and classify each one. Okay, so in terms of the classification of this carbocation, what is it? Primary, secondary, tertiary? Primary, great. Here, this isn't a carbocation, and a positive charge on a very, very electronegative thing is not stable. Does this make sense? Like bromine is very electronegative, and it wants all the electrons. So the fact that it has a positive charge indicating a deficiency is a very unstable thing. So I can kind of rule out this bridge as being the major contributor. But then if you look at this one, what's the classification of that carbocation? Secondary. Yep, secondary. Great. So now out of the primary and the secondary one, you can see that the secondary one is more stable for reasons we've talked about before. And that's why we always get addition at the more stable or more substituted position. And that corresponds to B. Okay? Does that make sense? Me proving it to you guys, hopefully. Yay. All right, I need to take like a water break real quick. So you guys let this digest and I'll be back in like a minute. All right, Caroline, can you explain your question a little bit more?
Yeah, so when forming the bridge, so the double bond is going to attack one of the bromines, and then, so can you just explain like that part, like what's bonding to what when we?
Yeah, I'll do it one more time, sure. So essentially what happens is that the nucleophilic pi bond, so there's 2 electrons in this bond, right? That's gonna form a bond, a carbon-bromine bond here, okay? Carbon-bromine bond here, okay? So that's what this arrow is indicating. So these pi electrons are going to form a bond to that bromine, and that's this bond, that's that bond, okay? Since we exceed the octet at this bromine now, because there's already 2, 4, 6, 8 electrons, and then adding these pi electrons makes 10, we have to break this bond, okay? And that's what generates this free bromide, okay? But remember, we say since the 2 electrons are completely being localized to this carbon to form that bond, we're gonna remove some of those electrons from this carbon at the end. So you get this kind of partial positive there. So the lone pairs on the bromine that was attached first is now also going to lean over and form that bond here. That's what this arrow is, okay? Does that kind of make more sense?
Yeah, so is there a reason why that bromine is going to attach to that secondary one? Is that because it's more substituted?
Yeah, exactly. And that's what we kind of just proved with this. And I'm going to show the next steps of the reaction. Yeah. All right, Lauren, so the carbocation in the example were only used because you were providing with a bromine. Exactly. I was just proving a rationale for why you would attack the more substituted position. But yeah, no carbocations really isolated here. There's no rearrangements possible. Yep. Yeah, so do the partial positive, that's why you get this kind of bridge structure, okay? Anyway, so now that was just one step of the reaction. So what happens now is the bromine is going to attack position B on both of these, and we explained why, because it's the more substituted, the more stable, electron deficiency to attack. Now, this is a very important thing in terms of stereochemistry for this reaction. I'm gonna write it like really big. Stereospecific, please remember that. This reaction is something known as is called stereospecific, and specifically that is known as, there's many different types of stereospecificity, and we're going to see different types, but the first one we're seeing right now is anti-addition. Okay, an anti-addition, and this is going to make so much sense, I promise. So what happens is this wedge, so again, with respect to that pi bond, we know it's planar, and we could have formed the bridge on the front face, that's the wedge one, or we could have formed the bridge on the back face, that's the dash one, okay? So that's why we have these 2 kind of isolated intermediates. If, let's just talk about this wedged kind of intermediate for a second, what you can think of is the wedge face or the top face of this molecule is sterically hindered by this bromine halonium bridge, okay? So the top face, like I'm sticking my hand up, the top face is sterically hindered and we can't access it. There's so much electrons, so much electron repulsions happening on the top face that the only thing that could happen is that this bromine comes and attacks the back face. So this bromine is actually going to come in on a dash. Do you see what I'm saying? The wedge tells me that I can't attack from the front face. I could only attack from the back face. Okay, so that means that this bromine coming in on position B is going to be a dash. And then this carbon-bromine bond, since we exceed the octet, is going to break. So the resulting structure I'm going to draw down here is going to be the dashed bromine that came in, and then this bromine just swiveled over and it's achiral at that position. These are the two hydrogens. Okay, so that's anti-addition. Here, because the bromine bridge is on a dash, it's going to come in on a wedge on the front face right there, break that bond and push the bromine over. So that should be something that looks like this. And that would be my two main products. Okay. A little bit more difficult in terms of like visualizing this, but I don't think it's anything too crazy. So the key things to remember, the more substituted position is where this anion is going to attack for the reasons we talked about in terms of carbocation stability. Specifically, we know that this is a stereospecific reaction because, oh yeah, so the reason why I'm talking about stereospecificity is because this is not a situation where I have to think, oh, am I going to get a chiral center and I have to generate, you know, wedges and dashes and do the wedge, wedge, dash, dash, wedge, dash, dash, wedge. We're not doing that here. You need to know how this reaction progresses because you specifically get these two structures, and we're not really doing that whole thinking to ourselves, how many chiral centers did I generate? How many major stereoisomers? We're not doing that here. This follows a very specific pattern, hence stereospecific, to get these two specific stereochemical arrangements. So yeah, there is stereochemistry in here. It's just we're not kind of doing the same logic or rationale that we did before. Okay. I feel like I kind of answered that, Caroline. So why not? So like it goes back to just like what I just said in the sense of this reaction follows this very specific pattern of addition. Like it just follows this pattern. Whereas the other ones, like we generated these carbocations, and then that gave us the opportunity to be able to attack the front of the back face. Here we don't really have these isolated p orbitals. So what happens is that we just react in this very specific way to get these two isolated stereochemical products. All right, no, one is not always going to be in plane. It's just in this specific example, okay? All right, thank you, Mary, that's awesome. Mary, you really know your stuff. I love that. Shout out to you. So let's just do an example of this reaction. So we're going to look at page 65, and we are going to be on letter P, so 11P. So we have a benzene ring. Okay, and we have this bond right here. And I'm going to just write CHCl3. So this is chloroform. So we're here. So again, remember that we normally assume that these two reagents interact together. But I told you at the beginning, there is no real reaction with this because it's an inert solvent. So all we have to really consider for all intents and purposes is the chlorine. Okay. So in terms of, you know, the first concerted mechanistic steps, remember it's the pi bond grabbing the chlorine, that bond breaking, and then the lone pairs from this chlorine fixing any deficiency to form a bridge. Okay. So here's a very good tip. I don't know if Dr. Peterson teaches it this way anymore, but this is how I liked to learn it when I was in her class. And what we did was we took this planar depiction, so it's flat. And you've seen me do this a couple of times, and I rotated it 90 degrees like that. So the resulting structure would be something that looks like this. So pH stands for benzene or phenyl coming out. The isopropyl is going in, the methyl is here, and I'll just draw the dash hydrogen. Okay? So that kind of all makes sense. All I did was I took this flat structure, I rotated it like this, and now that means that the benzene and the methyl are going to stick out at me, and then the isopropyl and the hydrogen are going to go into the board. Okay, so it's flat now. It's basically how I'm looking at it. And then whatever. Okay, so I think we're all good here. So the reason I did this is the chlorine bridge can form on the top. Okay, remember the top face of that pi bond, or it can form on the bottom face. So for what I typically do, like when I'm doing this quickly, is I would draw this structure. And I would also draw the other intermediate of where it's attacking from the bottom. It's still the same stereochemistry. Okay, so does everybody follow my two intermediates so far? All I did was I took this structure, okay? I rotated it, and then all I did was show that the chlorine can approach on the top of that pi bond or the bottom of that pi bond, okay? And that's kind of what we're seeing here. How do you know where the electrons go back to form chlorine? Like which carbon? Okay, so I guess it doesn't really matter, but in like what I'm just saying is that these pi electrons are going to form a carbon-chlorine bond here where the isopropyl group is, and then the lone pair here is going to form another lone pair carbon bond here. I don't know if that answers your question, Hal. Let me know if it doesn't. Okay, yeah. So we're here. And then the next thing we have to talk about is which position of this bridged intermediate is more substituted. Is it, this position or is it this position? Okay, so let's call this A, let's call that B. So out of position A or B, where am I attacking in the group chat? Or whatever, chat box. Let's see. A, we love that. Yay. Okay, so it's A because we see we have a tertiary position. We have, this carbon group down here, we have a carbon group here, and we have a carbon group to the right. So that's a tertiary position at A. Whereas at B, we have a secondary position. We have this carbon group and this carbon group. So that's secondary. So we always attack the more substituted side. So we would, excuse me. So we would have a chlorine anion that comes and attacks at that corner of the bridge. Okay? And then what happens is we exceed the octet now at this carbon, so this carbon-chlorine bond is going to break. Okay? So what I'm going to draw is this. So remember, the chlorine is coming in like that. Okay, so that's the first major stereoisomer that we're going to have. Okay, so do you see that? And the chlorine, this is the chlorine that came in, so I'll call that chlorine A. That's chlorine A. This was chlorine B originally. Okay, so what happened is that this chlorine came in from here, okay, and it attacked and it opened this bridge up. So you get this anti-addition. How is it anti-addition? I know you guys are going to hate me. Let's draw a Newman projection. So the front carbon, pH, back carbon, I'm just going to say iso. I'm just doing this really quickly. This is chlorine A, back carbon, chlorine B, methyl group, proton. With respect to the with respect to the chlorines, what is this type of conformation known as? Chat box, somebody want to? Anti. There we go. Anybody having bells ringing in their head? So yeah, it's specific. That's why this is known as a stereospecific reaction, because you're always going to produce products that follow a Newman projection that kind of looks like this. You're always going to have like these chlorines in anti-arrangement. Okay, so this is a very stereospecific reaction, and for that reason. Okay, anybody like that? Anybody come full circle? I don't know. Okay, so we have to talk about one more product. So this is the product from this intermediate, but we also can argue that the chlorine can attack at this position, okay? And then break the bridge open. So the resulting structure is going to be chlorine coming from the top, okay? You see we have that. The stereochem of the substituents stays the same. You don't have to change them, which is nice. And then you're there, okay? So these are the two products. And notice that if I were to flip them, so if I were to pancake flip this down, that these two chiral centers actually are not the same, they invert. So we have an RNS and we have an RNS inverting of configuration from the left structure and the right structure. So they are not the same, right? Yes, Caroline, what's up?
So you know how when you drew the two rings, so like for the first one, when the chloride ion attacks it, how did you know that was like going from like the bottom to up kind of direction versus
okay. Yeah. So you're always going to get a trans arrangement. So that may help you. So it's always going to be something like, or in terms of these really small short examples, so like either da 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 or da da da. Okay, so like you can see this one's already up, so clearly like I know it's going to swivel over. Like I know if this is my more stable position, this bond is going to break, and I think that's the key. So I knew that I was going to attack at this position, and this bond is going to break and swivel. Do you see what I mean by swivel? Swivels to the right when it breaks. So if this is swiveling to the right, what caused that? It was something coming in from the left. Okay, so that's that. That's kind of how I do it. Yep. And that's why the Newman is anti. We love that. Hear the bells. That's the whole point. It's not that hard if you guys understand it, which is cool. And I like that you guys have some bells ringing in your heads. I don't know. I like orgo. So next up. So let's do like a really simple one. Let's just do like 11R just to kind of ground us, and then we'll move on to the next reaction. So 11R, and we're going to definitely do more practice in subsequent sessions, so don't worry. BR2, you guys don't have your test for a while. Okay, so this is a pretty simple example. So again, BR. So what you can do is by your concerted arrows, so let's just say this pi bond is going to grab that bromine, break that bond, and then these lone pairs are going to come back and fix that deficiency. We could argue that we have, you know, the bridge forming on the top face. And we could also argue that we have the bridge forming on the back face. And if you're looking at this, what are we thinking? Or do we think that these two intermediates are identical? Do we think these two are identical? I'm looking for a specific word. It's a type of soup. Yes, love it, miso. So because these have a plane of symmetry, and you could basically flip them over, these are the exact same intermediate. So we only have to really consider one. So that's cool. And what we can do now is that the bromine, okay, and there's no difference in substitution, so that's also a nice thing here. That bromine is going to attack there, give those electrons there. But now remember, if I'm considering this wedged one, if I'm considering this wedge structure, that bromine can only come from the back on a dash, and that pushes this over. So essentially, you know, here you would have dash bromine, wedge bromine, okay? And I'm going to take you guys a step further just to make some more bells go off in your head, okay? I'm going to call that one. I'm going to call that two. You guys know where I'm going with this. 1 and 2. Does the stereochemistry on 1 match the trend for 1? No, it doesn't. So that's equatorial bromine. Same for 2, equatorial bromine. Let's draw my ring flip. I think a lot of orgo students often forget that they have these tools that you can use to help you with rationalizing things. So we're there. So in this specific chair conformer, which is relating to the product we drew, do you guys see how the bromines were added anti-addition? I hope we see that. One bromine's up, one bromine's down. They're 180 degrees apart from another. So again, this is still an example of anti-addition. Anybody like that? No, I don't know. Okay, so that's that. Let's move on to Halohydrin synthesis. I think we have like 3 minutes left. Hal, LOL. All right, let's go to Halohydrin synthesis. So this is like where we're going to stop today. So we're going to do one more reaction. Definitely, we covered a lot of material today. So now the difference with this one, and again, it's just another variant of the one we've seen already. So instead of having, before we had X2 and then some sort of inert solvent, let's just say DCM, we're going to replace that inert solvent. Now it's no longer inert, and we're going to place it with water. Okay, water. Okay, this is kind of like a variation of acid catalyzed hydration and the halogenation ones that we've seen. So essentially what happens is you still get the exact same bridge forming. So in terms of just like, you know, proving this to you, we're still going to get a Helonium bridge. So I think that makes sense now. Something like that. Okay, so we get this Helonium bridge. But now it's not the X minus halide coming in. That's not happening. Water is going to come in. And it's water that's going to break open the bridge. Okay, so it's the exact same thing we literally just did. But now it's instead of the X minus ion going in, it's water going in. Why do I know it's water that's going in? Let's think about our trends, okay? Let's think about our trends. Remember, everything makes sense in orgo, so if you don't understand it, let's go back to something we don't know. Let's think about electronegativity. So for a halogen, how much does it want to hold on to those electrons? Would we say a lot or a little? A lot. I love that. So a lot. Let's just do that. For water, and specifically I'm talking about the oxygen, in comparison to the halogen, it's less electronegative. So we could just say like a little. Okay. And remember, nucleophiles, these nucleophiles are giving off electrons, giving electrons. So you can see how water is giving electrons, can give electrons easier because it's less electronegative than the anion would be. So that's why water, even though anion is generated, water is more nucleophilic, and water is going to attack these positions a lot more than those anions would. How do you know it was on a wedge? I just assumed it was on a wedge. You also get this one. You also get this one. I just didn't draw both. You also have that one. Okay, so you can see that water is going to be more nucleophilic than the anion would be. So it's the exact same thing. So you can rationalize that if water is going to come in, let's just draw this product down here. If water is going to attack there, your structure should be something that looks like, for that example, and I'll explain how you get rid of that proton in a second, very similar to acid catalyzed hydration. And then you could also get from this guy, oops, sorry, OH. Okay, so what a halohydrin is, it's another functional group. So you guys have learned a couple of functional groups so far. There are way more that exist in the real world than the ones that you've had to memorize. So what a halohydrin is, it's this. So halohydrin. Halo meaning halogen, hydrin meaning hydrate, and it's specifically referring to a molecule where that hydroxyl group and that halogen are just adjacent to one another. So halohydrins are functional groups where an alcohol and a halogen are adjacent to one another. Okay, so this is pretty much the exact same thing. So let me just draw quickly the mechanism and then we'll be done. So I'll just do an example of that. This would be, let's just do U, so 11U. And we're gonna look at this one. And we have this. So now for all you guys thinking about stereochemistry, you can see that this wedge is already provided. Doesn't look like we're gonna react there. So all of your end products should have a wedge with that methyl, with respect to that methyl group. So what we're gonna do is we're gonna subject this to bromination conditions, so Br2 and water. Okay, so what that means is Br, and Br is here. Pi bond grabs, breaks the octet, lone pair fixes that deficiency. We can isolate two different intermediates. Remember, because this methyl group is here, it's no longer meso. So we have to consider both. So Br plus, and then here, Br plus, and that's the same. Okay, also, there is no difference in substitution. So we kind of argue that the water can attack at either position. So here, we can say that water is going to come in and attack here and break that bromine bridge. And we could also say that water here is going to attack this position, okay, and break the bromine bridge. So that's that. Oh, there's no methyl group? I'm confused. Wait, let me read those questions. Caroline, what are you talking about with the methyl?
Like the methyl from the original structure?
Oh, it's not in your problem? Is that not in your?
It is, but is that not like added on to the intermediates?
Oh my God, I didn't even see that. Oh, I'm so sorry. I didn't even see that. Thank you. Wow. Okay, yes. Thank you, Caroline. I appreciate that. I didn't even recognize it. So there is a substituent here. So if I were to decide to form the bromine bridge on a wedge, that pushes this substituent back to a dash. Likewise, so actually this changes this whole problem. I apologize. So essentially, I'm sorry, I messed that up. Okay, and we're here. So, my bad. Okay, so we're there. So essentially, what happens is we're gonna have water now attack the back face of the molecule, okay? At the more, for this one specifically, the back face of the molecule, specifically at the more substituted side of it, okay? More substituted side, and then break the Helonium bridge. So essentially, the stereochemistry, watch this. This is going to be very a lot of detail here. So since the water came on the back face, that means it's going to be a dash. Okay, so that's dash, OH, OH. That's water. Since it came on a dash, that methyl group is now forced to become a wedge. And then now this bromine bond broke, so the bromine is now hanging out over there. One final step in terms of mechanism is assume excess, water to remove that final proton, and you synthesize your halohydrin. Okay, so that's one major product. And then the same thing happens for this guy. So for water, it's going to attack, the more substituted side, and it's going to break that bond. So essentially, I'm going to skip this step in the middle, but you should get stereochemistry that looks like this. So with respect to the halohydrin, so the bromine and the hydroxyl, those two substituents with respect to their stereochemistry should be the opposite. So one should be wedged, one should be dashed, one should be wedged, one should be dashed. That indicates the anti-addition was successful. Okay? Mic drop, everybody. So yeah, that was orgo overload. I think we got to a good place. So you guys should watch today's lecture. I think it's on oxymercuration and hydroboration conditions, and we'll pick up with those two reactions next week. Okay? Yeah. Yep, Leah, the other bromine stays in solution. And I'll upload the rest of these YouTube videos today. All right? See ya.